Our universe is a strange and wonderful place. At the smallest level, it's governed by rules that defy common sense. These rules belong to the realm of quantum mechanics, a theory that has revolutionized our understanding of the cosmos. Quantum mechanics deals with the very tiny atoms, electrons, photons, and other subatomic particles. These particles don't behave like anything we experience in our everyday lives. They can be in multiple places at once. They can act like waves and particles at the same time. It's enough to make your head spin. But don't worry, we'll navigate these strange waters together. This essay will be your guide to the fascinating world of quantum mechanics. Both. That's right, light is both a wave and a particle. But how can that be? Let's dive into this fascinating topic and unravel the mystery of light's dual nature. Let's start with a simple question. What is light? Light is a form of energy that we can see with our eyes. It's all around us, from the sunlight that brightens our day to the artificial lights that illuminate our nights. Is it a wave or a particle? This question has puzzled scientists for centuries. Light seems to have properties of both waves and particles, but how can it be both at the same time? For centuries, scientists debated this question. Some of the greatest minds in history, like Isaac Newton and Thomas Young, conducted experiments to understand the true nature of light. Some experiments showed light acting like a wave, such as when it passes through a prism and splits into a spectrum of colors, much like water waves creating patterns as they move, while others showed it behaving like a particle. For instance, when light hits a metal surface, it can knock out electrons, behaving like tiny particles called photons. Then came quantum mechanics, which provided a surprising answer. Light is both. This revolutionary theory changed our understanding of the universe at the smallest scales. This mind-bending concept is called wave-particle duality. It means that light doesn't fit neatly into the category of just a wave or just a particle. Instead, it can exhibit properties of both, depending on how we observe it. Light can act like a wave when it travels through space, spreading out and creating interference patterns, much like ripples on a pond. But it can act like a particle when it interacts with matter. For example, when light hits an object, it can transfer energy in discrete packets, or quanta, known as photons. Think of it like a coin. When you flip a coin, it spins in the air, showing both heads and tails at the same time. This is similar to how light can exhibit both wave and particle characteristics simultaneously. When you flip a coin, it spins in the air, showing both heads and tails at the same time, but when it lands, it can only be one or the other. This is akin to how light behaves, but when it lands, it can only be one or the other. Similarly, when we observe light, we can only see it as either a wave or a particle, but not both at the same time. Light is similar, it has the potential to be both a wave and a particle, depending on the experiment and how we measure it. But we only observe one aspect at a time. This dual nature of light is one of the most fascinating and mysterious aspects of quantum mechanics, challenging our classical understanding of the universe. Another strange aspect of the quantum world is the Heisenberg uncertainty principle. This principle states that we can never know both the position and momentum of a particle with perfect accuracy. The more precisely we measure one, the less we know about the other. Imagine trying to track a tiny, fast-moving marble in a dark room. If you use a bright flashlight to pinpoint its location, the light will bounce off the marble, changing its speed and direction. The act of observing the marble inevitably disturbs it. The same is true in the quantum world. Our attempts to measure a particle's properties inevitably affect its behavior. This isn't a limitation of our instruments, it's a fundamental law of nature. One of the most bizarre concepts in quantum mechanics is superposition. This principle is a cornerstone of quantum theory, and has puzzled scientists and philosophers alike for decades. It challenges our classical understanding of reality, and forces us to rethink how we perceive the world at the smallest scales. This principle states that a particle can exist in multiple states at the same time until it's measured. In other words, a particle doesn't have a single definite state but rather a range of possible states. This phenomenon is not just theoretical, it has been demonstrated in numerous experiments showing that particles can indeed be in a superposition of states. It's like a coin spinning in the air. It's both heads and tails until it lands. This analogy helps us grasp the concept, but in the quantum world, the reality is even stranger. The coin doesn't just spin, It exists in a state where it is simultaneously heads and tails, and only when we observe it does it choose one outcome. A famous thought experiment illustrates this idea, Schrödinger's cat. This thought experiment, proposed by physicist Erwin Schrödinger in 1935, was designed to highlight the peculiarities and paradoxes of quantum mechanics. It has since become one of the most well-known and frequently discussed concepts in the field. Imagine a cat inside a box with a device that has a 50% chance of releasing a deadly poison. The device is triggered by the decay of a radioactive atom, which is a random process. If the atom decays, the poison is released and the cat dies. If the atom does not decay, the cat remains alive. This setup creates a situation where the cat's fate is intertwined with the quantum state of the atom. Until we open the box, the cat is both alive and dead simultaneously. It exists in a superposition of states. This means that the cat is in a mixed state of being both alive and dead, and it is only when we open the box and observe the cat that its state collapses into one of the two possible outcomes. This thought experiment vividly illustrates the concept of superposition and the role of the observer in quantum mechanics. Only when we observe the cat does its state collapse into one definite outcome, alive or dead. This collapse of the wave function, as it is known, is a fundamental aspect of quantum mechanics. It suggests that the act of measurement or observation plays a crucial role in determining the state of a quantum system. This idea has profound implications for our understanding of reality and has led to various interpretations and debates within the scientific community. While we can't perform this experiment with actual cats, ethical concerns aside, scientists have observed superposition in the lab with atoms and other particles. These experiments have provided strong evidence for the existence of superposition and have helped to advance our understanding of quantum mechanics. By studying these phenomena, researchers hope to unlock new technologies and gain deeper insights into the fundamental nature of the universe. The strange behavior of quantum particles is perhaps best illustrated by the double-slit experiment. This experiment, first conducted by Thomas Young in 1801, was originally designed to demonstrate the wave nature of light. However, when it was later adapted to test the behavior of electrons, it revealed some of the most perplexing aspects of quantum mechanics. In this experiment, electrons are fired at a barrier with two slits. These electrons, which are subatomic particles, are expected to behave in a certain predictable manner, much like tiny marbles being shot through the slits. Behind the barrier is a screen that detects where the electrons land. This screen is crucial because it allows scientists to observe the pattern formed by the electrons after they pass through the slits. If electrons behaved like tiny marbles, we'd expect to see two bands on the screen, corresponding to the two slits. This is because each electron would pass through one slit or the other and hit the screen directly behind the slit it passed through. But that's not what happens. Instead of two distinct bands, the pattern on the screen is much more complex and unexpected. Instead, we observe an interference pattern, a series of light and dark bands, as if the electrons were waves interfering with each other. This interference pattern suggests that each electron is not just passing through one slit or the other, but somehow passing through both slits simultaneously and interfering with itself. Even stranger, when we try to observe which slit each electron passes through, the interference pattern disappears. This phenomenon is known as the observer effect. The act of measurement itself seems to alter the outcome of the experiment. It's as if the electrons know they're being watched and decide to act like particles instead of waves. This change in behavior when observed is one of the most baffling aspects of quantum mechanics and challenges our understanding of reality. This experiment highlights the profound strangeness of the quantum world and the role of observation in shaping reality. It raises fundamental questions about the nature of particles, waves, and the very fabric of the universe. The double-slit experiment remains a cornerstone of quantum mechanics, continually inspiring new research and debate among physicists and philosophers alike. Quantum mechanics might seem like a strange and abstract theory, but it has had a profound impact on our lives. Many of the technologies we rely on today, lasers, transistors, computers, smartphones, wouldn't exist without our understanding of the quantum world. Quantum mechanics has also led to groundbreaking discoveries in other fields such as medicine, material science, and energy production. And the future of quantum technology promises even more exciting possibilities. Imagine a world with unhackable communication networks, ultra-powerful quantum computers, and even teleportation devices. While these ideas might sound like science fiction, they're rooted in the reality of quantum mechanics. The future is quantum and it's full of endless possibilities.